So welcome back to another video, guys. Today we are making our units move on a 3D mesh inside Godot. We're going to add a label 3D and inside the node 3D, and you can see how the agents will avoid it. And this will take us one step closer to making an RTS project. So let's add our navigation agent and remanage our nodes here. We'll start by the test unit here, and I'm going to change the scene root to be our character 3D, make scene root, and now we can remove the script from this node. And let's put these nodes inside the character 3D. And now we can delete our test unit here. Now we have to attach that script back. So let's do a quick load to our test unit script. Now, another thing we are going to have here is we are going to add our navigation agent, and this is the guy that will be responsible for everything we're going to do navigation-wise. So now our character has a navigation agent which we are going to use. So that is all for the nodes. So now let's go through step 1. We want the player to click somewhere in the map, then we are going to cast a physics raycast against the map. From the camera origin to the mouse click position in the 3D world. If the raycast reads something, that position we are going to use as a navigation goal, so we are going to need to create a new module for that, which is going to hold the raycast operation. So let's go here and let's add a new module, which is a simple script, just like in previous tutorials. So let's go right ahead, and this is the module camera. So you want extending ref count. And this is going to hold camera operations, just a simple description there. So let's go ahead and let's create our function, our main function, static func, and it's going to be a get vector 3 from camera raycast. And this function is going to ask a couple of arguments here. We want first our camera, which is a camera 3D node. We also want some 2D coordinates, which you are going to use here. So camera 2D coords, which is a vector 2. And this function doesn't return anything else than a vector 3. And this vector 3 is going to be the position of the raycast collision, if any. If not, then we're going to return a vector 0. So we can later change this to return the dictionary if we want to do something different, but for now that's the idea. So we are going to start here with a variable, which is going to be ray from, and this is a vector 3, and we're going to grab from the camera its origin through the 2D coordinates. So camera dot, and I believe it is projects ray origin. There we go, and it's going to ask for those 2D coordinates. So camera 2D coords. Now the ray target is going to be ray 2, I'm going to call it, and it's a vector 3. And it's from the camera as well. It's a function from the camera, and just like the other one, we are going to do project normal. However, here we also need to add the ray starting position, so it goes like this. And here you can also pass this camera 2D coordinates. So now we have a ray starting and ending position for the raycast. So now we are going to need to generate these as a raycast physics parameter. So for our ray parameters, they are of the type physics ray query parameters 3D. And we are going to generate a new one by accessing the same class, ray query parameters 3D, and we are going to say new. Now, new allows you to add exactly what we want here. So if we're going to create, and is actually create, you can see we can give the from and ending points. Otherwise, you have to access as a variables. So if you go to properties, you can see here the from and to are inside this physics ray parameters object. So you can actually use that function create to put the arguments inside here already, and it's going to generate them for us. So ray from and ray to. If we press Ctrl space bar here, we can see that this is the second argument and it's correct, and the first one is ray from. So that generates us some physics ray query parameters, which we are going to use next here. This variable here is the result of the collision from the raycast operation. So this is actually a dictionary, and we do this accessing the camera Then we are going to get the 3D world. Then we are going to act direct space state, and from that function we are going to cast the array we want. So this is the moment where we ask the intersect array. So all of that we did is going to be inserted here, because this function requires a physics ray carry parameters 3D, which is the one we did right here, the ray parameters variable. So we can pass that through here. So now it's going to cast a intersect array. So this is going to cast a physics array from the origin to our goal, and it's going to return a dictionary. So if we do a quick check here, so it's going to return a dictionary with a collider ID, but what we are interested in is the position. So we're going to say here, if we have any results, so if the dictionary actually has some values, we're going to return the result dot position, so where we actually hit something. Otherwise, we're going to return a vector3 0 position, and I can actually put this in a single line. So this is actually how the function is going to work. So we are going to turn our mouse position as a raycast operation in the 3D world. So let's save this, and I'm going to copy the name of the function here. So now that we have the camera function we are going to use to project the mouse position, let's go to our test unit and actually program here our input function for the left mouse button. So let's start with the function input events, and this is a input event, and this function returns nothing. So the first thing we're going to say is ask if the input we are getting is an action that just got pressed. And I don't know if we have, yes, we have a mouse left click. So if we go to project settings and we go to the input map here, you can see mouse left click, and it's the mouse left button. So that is something we want here. So if we left click somewhere, we're going to retrieve the mouse position first. So the mouse position is a vector2, and we are going to grab it as a get viewport dot get mouse position. This is one of the ways you can grab the mouse position. Next, we're going to need a camera. So one of the ways you can grab a camera node without having to reference from a auto load, a global node, etc., is you get from the viewport the get camera 3D. So this function is going to grab the viewport and is going to search for any active cameras, and it's going to return as a camera 3D. Here returns the currently active 3D camera, and this is what we want. So now we need the raycast parameters from our module camera. So let's load our module here. So this is our module camera, and it is a GD script. So we had an issue with this previously, but I believe now it's fixed. It was a series of game data, and I don't know if updating made any changes. I think it fixed. I'm using the 4.3 RC1, so I don't know if that fixed, but it seems to have fixed. So let's do preload, and here you put the module camera. Now we can actually access our camera here, our camera function. So the raycast we're going to get is a camera raycast coords. And this is, so where we clicked our mouse, if we collide with something with a raycast from the camera to the mouse position, it is going to return here as a coordinates. So we're going to say that is equal to our module camera. And then we are going to put it here, that function we just created, which was vector3 from camera raycast. So we want to cast the raycast with our current active camera, and we're going to pass our mouse position as the 2D coordinates. So now you're going to ask here something. If our camera raycast coordinates, it's going to be different than vector 0. So we return 0 if we didn't found any collisions whatsoever. So with this, we are going to discard any other raycast operations that did not collide with anything. And now we are going to ask for our navigation agent, which I did not add here as a node. And I'm going to put it after the constant. So let's throw in here our navigation agent. So already var nav agent, which is a navigation agent 3D. Then we can do here nav agent dot, I believe it's set position, set target position. Let me double check. So it is target position, set target position. So we're going to give the position that we collided with the raycast camera. So camera raycast coords. So with this, we now have a target for our navigation agent, so it can generate a path here. So this concludes the step 1, which we now have an input command that is going to return us a location where our mouse click hit something physically. So this is the step 1 of our procedures. Let's save it. Don't forget to save. Now, if we go back to our 3D scene here on the world, we can see some things here. This 2D area 3D here is for our visible units. And I don't think we need this to be visible to work. We have to do some testing later. But you can see that this world map here is only a mesh instance. There's no actually colliders here. So this will not work if we wanted to move our units. So let's create here a static collider, which is a static body 3D. And it's going to ask us for a collision shape. So let's give a collision shape 3D. And I'm going to create a new shape here, which is going to be a box. And I believe it's 20. Yeah. So 20 by 20. And I'm going to place it below the ground here. Just by moving the collision shape 0.5 negatively. There we go. Now we put the collision shape inside the static body. And now we actually have a map that's going to hit with our raycast from the mouse, which is what we want. So let's save this. And one of the things I want to do here is go to our test unit. And I'm going to print these coordinates just to see if it's working. So the camera raycast coords. Let's just save. Let's see if you get any errors or something. And we are getting some print commands here. I believe it's from our player interface. It's from this guy here, the book units visible. So the visible area 3D we just created can work while still not being visible. So this is good news for us because we can keep it hidden and still worked. So, and as you can see, it's adding the world node 3D. We don't want that for our RTS selection. Cast selection, I believe this is going to throw an error. Yeah, if you click, you're going to get an error. And this error is because there's no deselect mesh instance. So because of the colliders getting added as a selectable unit. So for now, what I'm going to do is on our player interface script for the units in cast selection, first thing is if unit is a character body 3D, then we're going to proceed to select it. So this is a temporary fix. We do not select the floor of the world, so now it should not give any errors. And as you can see, it's not working because we are going only 0 coordinates. So it seems that I have forgotten here on the ray 2, I forgot to multiply by a ray length distance. So what is happening is because we are not using this result of the ray is too short for us to actually use it. So what is happening is we are actually projecting the ray correctly, but it's too short. So it's ending almost here and there's no collision between these 2 points. So if we multiply that result from the target of the ray by 1000, it's going to take the short 1 unit and multiply by 1000. So it can actually hit something that way. So if we actually test this scene, we might actually see some stuff here. And as you can see, that was the issue. My bad, I forgot to add that. So now it's working. So let's go through step 2 now, updating the nav agent algorithm. We want for each physics frame to let the agent set its velocity towards the next path position. So now let's go ahead through step 2, which is now updating the nav agent algorithm in the physics process. So let's go to our test unit here through a physics process function. So this is a physics process, delta is a float, this function does not return anything, so void. So the first thing we're going to do is ask for a next position for our navigation. So next position, it's going to be a vector tree, which is from the nav agent get next path position. So we are going to say what is actually the next position. So let's calculate the nav agent next velocity. So the first thing we want is a direction. So the direction is a vector tree, and we're going to grab this from our current global position with the direction to our next position. And that is how we are going to grab our direction. Then the next thing we want is to multiply this by our nav agent maximum speed. So we're going to use the max speed of our agent. Now this should give us a direction to go. So now that we have our direction, we can create a new agent velocity, which is going to be computed inside the navigation one. And this is going to be our velocity plus our direction minus our current velocity. So identify our velocity not declared. So you can see that's because we're extending from Node 3D. And Node 3Ds don't have velocity, but character bodies 3D have velocity. So we will get recognized. So this is our new agent velocity. And now we just need to finally add this as a new velocity for our navigation agent. So our navigation agent needs to set this velocity with a new agent velocity. This concludes our step number 2. So now we'll have once calculated our safe velocity, avoiding obstacles. We need now to go through step 3, which is all about actually moving our character 3D node after the safe velocity is emitted. So now we actually have a new velocity for our navigation agent, but this set velocity needs to now pass that to a signal, which we are going to use now. So from the navigation agent, we have the safe velocity, which is gets computed. So it's computed velocity. There we go. So when you set the velocity, it's going to, on the navigation agent, it's going to send a velocity to the collision avoidance algorithm. But what's important here, it is going to emit a velocity computed signal once the adjustment to the velocity is completed. So this velocity computed is actually the place where we can actually move that has passed through the navigation algorithm. So if you go right here, so let's create a new function here, and this is going to be sharp move. And we are going to simply move the character with this one. The first thing we want is a vector tree, which we want to move our character. So let's go here, new velocity, which is a vector 3. So this sharp move is going to be connected with our velocity computed. So let's connect to our sharp move, and velocity computed passes the argument of the new velocity. So what our character actually have to do is simply get the velocity and set it as a new velocity. And we do a move and slide, which is pretty standard for character bodies 3D. So I believe that only these codes should be enough to move our units. So I'm going to mute the print here. And if you run our scenes, nothing is happening. So we are missing something. So something I forgot to assign here. All of the code for our test unit here on about set velocity. So set target position, this right here, velocity computed. So notifies when the collision avoidance velocity is calculated. So collision avoidance. So this is only emitted in the case when the avoidance is enabled. And guess what? I forgot to set it up. So that is why it didn't work. So if you see here, avoidance enable. So now the units should move. Now the last thing we need to add here is the navigation map itself. So let's create a new node. And this is going to be the navigation region 3D. So this is actually the map that's going to create our navigation mesh. So let's generate a new navigation mesh. And let's drop our floor inside the navigation region 3D. Then the last step is just for you to bake the new navigation mesh. So with this information, now the navigation agents should actually move on their 3D scene. And as you can see, they are moving. But we have a couple of issues here. One of them is they don't stop. So once after they move, they never stop and they continue to infinity. A temporary fix we can do is on the physics process. So let's go our test unit here on the physics process function. We are going to ask if navAgent dot finish navigation finish no is navigation finish. There we go. So if that's the case, we are going simply to return. So with this now, our navigation agent, once it has finished the navigation, it should stop instead of actually trying to move. So we have a couple of issues here. One of them is that the units are floating. So as you can see, it's quite a big float. It's not small. And how do we fix this? Well, that is because our navigation is generated by standard some units above the floor. So you should not lower the navigation mesh by going here to cells on the height, putting 0. So when you generate the mesh, it's going to fix it because this helps in some instances. So what you can do instead with the navigation here is go back to our units, and on the agent, there is on the pathfinding algorithm, there is a offset here, which you can set to 0.25, which is the same for our navigation region here. So now if we run our scenes, we should not be able to see that height difference, which as you can see has fixed the problem. Now another issue we are having is the collision shape is not suitable for our units anymore. Instead of box, we're going to use capsules, which allows units to slide instead of getting stuck. And I'm going to reduce the radius here by 3.3, and the height, I believe 1.2 might work. And 0.6, there we go. So now the units are optimized a little better, and they should move a little easier. And they are faster to slide along because squares, they get stuck one another. And as you can see, there we go. So one thing we can do here to make this a little more fun is go back to our units and let's add here a steering behavior. So let's create a new variable here, and I'm going to call this steer speed, and this is a float. And let's put here 4.0. So for us to steer our units, we are going to come down here and we're going to create a new variable, which is going to be steered velocity. And this is our direction minus velocity, just like down below. However, here we're going to add delta. So this is going to slow down a bunch. And here it just adds the steer velocity. And here we can multiply it by our steering speed. So I'm going to show this with a low value here. If we run our scenes, you should see the units trying to steer along. And this can create behaviors as you want them. And I think it looks a little more realistic. Obviously, the steering speed is very low. That's why you see them maneuvering one another. With big arcs, what you can do is increase the steering speed to something like 4. Then they will move a little more predictable. And it is almost the same, but they are actually trying to maneuver their velocity to their target velocity, which creates the steering velocity. So this is a little bit better. And this is pretty useful if you want to make like spaceships. You should be able to decrease the steering speed to make them create those arcs we just saw. So this is pretty fun now. So one of the issues we have with this, if I go to debug here, collision shapes and navigation. If we run our scene, we can see the navigation polygon here. But okay, we are not seeing what I wanted to see. I believe it's because it's on the navigation agent. So there's a debug function here on the navigation agent itself. If we enable this and we run our test scene, we should not be able to see the path the navigation is taking. So as you can see, there's an issue here. Our path never gets updated once requested. This works when the player asks for the unit to move somewhere that doesn't change. But if we ask it for a unit to follow another, the path needs to get updated to the new unit position. So we need to keep updating the navigation path in order to make sure our destination goal hasn't changed. So this is a big issue if you plan to make your units follow a movable target. So it needs to be updated. What you can do is to create a timer. So we are going to create a timer node, and I'm going to put it here as 0.25, and it automatically should start. So this timer we are going to use to recalculate the navigation agent's next position. So you're going to need a couple of things here. The first one is our timer node. So this is navpath timer, and there we go. The next one we're going to save is our goal position. So our navpath goal position, and this is a vector 3. So now what we can do is assign our destination here to our goal position. So it is camera raycast coordinates. So now we are actually saving our navpath goal position. And what this allows us is to create a new function for our timer. So navpath timer update, and this function returns nothing. And what we're going to do is simply copy this, but now instead of updating to the camera raycast coordinates, we're going to update to a navpath goal position. So what this is going to allow us is to update our path whenever the time runs out, and it's going to update the target position of the navigation agent. And we're going to say the same thing as this guy. If we, however, finish our navigation, then we're going to simply skip this function, so it does not print always. So if you run the scene, now we should be able to see the unit's path. And I forgot to put the connection code. So let's go back to our units and connect our timer here. So it is the navpath timer dot timeout connect, and the name of the function is navpath timer updates. Now it should work. Yep, and as you can see, now the units are automatically updating their path to the goal destination. And this is something we want, because now we can assign a movable target and the units will work accordingly. So this is the first step into making an RTS movable units. We can actually disable the collision navigation so we can actually see the units moving. And as you can see, pretty fun stuff. And that's pretty cool. One of the things you can change here is also for the navigation agent, for the radius of the units, to put the same as the collision shape. So the collision shape radius is 0.3. So this allows your units to be more smaller in the navigation agent. And as you can see, it works a lot better now, because they are not 0.5, they are 0.3. But you can also increase that to make your units not collide with one another. And because this is a character body 3D and not a rigid body, they do not push one another. And that is for performance reasons. We can do areas 3D here to push units, and we'll see about this later. For now, this should provide you with the basic infrastructure to move units. And the last thing I'm going to do here is just to rotate our units. So on the code that moves our unit on the test unit here, the character move, we're going to create a simple function here. And it's going to be the rotation of our units dot y is going to be equal to a mathematical function, which is a10. And we're going to pass here our velocity x and velocity y. And it's going to pass our position, and I put here something else. There we go. So if we run our scenes, you can see something pretty cool now. Our units now are actually rotating to their movements. And yes, this is because it's trying to move to the destination here, but there are 2 character bodies. So this will be fixed whenever we push our units. But as you can see, it's working accordingly, which is pretty fun. Now the last thing is for us to test the collision avoidance algorithm. So how we are going to do that? I'm going to create here a navigation obstacle 3D. And I'm going to place this inside a node 3D. Now this node 3D is a collision avoidance. So if we put here a label 3D, and let's give some text like collision avoidance points. And I'm going to rotate it a bit. Now if we push this node a little bit on top, now the other units should avoid this guy. Now the interesting part of this is this navigation obstacle now will be avoided by our units. And as you can see, it works. So how it works is the collision avoidance algorithm treats this point as a sphere and will make our units move alongside it. And this is done dynamically. So if we remove our collision avoidance points, it is going to also move the algorithm dynamically. So this works in real time. And as you can see, it's pretty interesting. So you can make units avoid dynamic targets, just like I showed in the demo. So there we go, another step closer to our RTS project. Thank you for watching this video, and I hope you find it useful. Like if you liked it, comment if you have any questions, and I'll see you in the next video. Bye for now.